Okay, we were just introduced to a whole bunch of formulas that are going to make our life a lot easier. Instead of using the limit definition to derive all of these formulas for these differentials, we're going to be able to do it using the formulas. But first, we must prove that they are valid. And in order to prove that, we have to use the original limit definition for the derivative. So the derivative of a function, f of x, is equal to f prime of x, which is a limit as h approaches 0 of f of x plus h minus f of x plus over h. And we're going to use that to prove each of our formulas. So let's get started. Once we do it, we don't have to worry about it anymore, and we can just use these formulas freely. The first formula, number 1, prove the derivative with respect to x of a constant function c is 0. In other words, when our function is f of x equals c all the time, no matter what x is, the constant function, that's always going to give us a 0 derivative. Let f of x equal c for all x in the real number. So it doesn't matter what x is, f of x will be c. Then the derivative with respect to x of this f of x is equal to the limit as h approaches 0. That's a typo. It's h approaches 0 of f of x plus h minus f of x over h, which is equal to the limit of c minus c over h. Why is that? Because it doesn't matter what you evaluate the function at, it's always going to equal c. So we get the limit of 0, which is just equal to 0. Number 2, we're going to prove the derivative with respect to x of a constant times the function is equal to the constant times the derivative of the function. In other words, you can pull constants outside of the derivative operator. Let's prove that. Prove derivative with respect to x of c times f evaluated at x is equal, according to our limit definition, to the limit as h approaches 0 of c times f of x plus h minus c times f of x over h. We're just applying this function to the limit definition. Well, what is that equal to? Well, we know something about limits. We can pull constants outside of limits. Okay, so let's just factor the limit out of the quotient ratio, and then there's our dotted arrow reminding us we can pull constants out of limits all day long. So we pull it out of this particular limit, and it gives us c times the limit, but that's c times the derivative of f, and that's exactly what we were trying to prove. So we're done with that one. We're finished. Let's go to step 3. Prove the derivative of a product f times g is equal to the function f times the derivative of the second function g, plus the function g times the derivative of the first function f. That's kind of strange, but at least it's symmetric. Let's see if it's true. This one's a little long. The derivative with respect to x of the product f times g of x by definition is equal to the limit as h approaches 0 of the f function evaluated at x plus h times the g function evaluated at x plus h minus f of x times g of x over h. Yes, that's true. All right, now we're going to do something very weird. We're going to plug something in here. Everything's cool, but now look what we're doing. We're subtracting f of x plus h times g of x and adding f of x plus h times g of x, and then we have the stuff at the end that we had before, f of x g of x. But I want you to notice, this is over h, that what we've done in the middle is nothing. That's all equal to 0. So we did this just to set something up, but we haven't changed the value of the quotient function. Now we're going to factor out the f of x plus h and the g of x. So we have, okay, we're setting it up for what we're hoping to get. This is the limit of f of x plus h. Now, what did I factor it out of? I factored it out of the g of x plus h minus the g of x, okay? And I put all of that over h. Then I'm adding, factoring out the g of x. What do I factor that out of? I factored that out of f of x plus h minus f of x. All right, bracket over h. It's just math. It's just algebra, factoring. Now, I'm going to distribute my limit. So the limit of the first factor times the limit of the second factor, that's valid. We know that about limits. We can distribute limits across multiplication, plus the limit of the next first factor times the limit of the other factor. Okay. All right, so we're just distributing the limit across multiplication of factors. Now, notice that the limit of g of x is independent of h. It has no h in it anywhere. Keep that in mind. So the limit of f of x plus h, that's just f of x. And the limit of g of x plus h times g of x over h, that's the definition of g prime of x. Plus, this guy's independent of h, so he just comes out in front like a constant. He's g of x times the last guy, he's just the definition of f prime of x. You might want to pause the video and meditate on that one because it's all there and it's all good. The derivative number 4 of x to the nth power is difficult to do here, so I'll let you check that one out on the text. In the text they have that one worked out, and it's a little bit difficult. But there's still more to go. We have to prove some more of these limit formulas, so we will continue on our next video.